Hello everyone. This video lecture is about digital electronics. Logic design is one of the favorite topics of many companies which come for electronics and communication placements. Even different some companies might ask these questions to electrical and computer engineers. Understanding of, particularly for electronics graduates, understanding of digital and analog circuits becomes very important. So, I'll go through the fundamentals of logic gates in this video, and in the end, we'll just run through some types of questions that are asked in placement interviews to give you an idea on what level you should you must prepare for your campus placements. Getting started with it. Let's start with the fundamentals of logic gates. In the this video, we will be going through understanding of the common types of logic gates, truth table, and I'll also touch base some fundamentals of types of circuits, etc. So let's get started. The first thing here is understanding of what is a gate. So gates are building blocks used to create digital circuits. We call them logic gates. Internally, there are a combination of transistors that perform binary logic. It's all a game of zeros and ones as we know it. So there are three elementary logic gates and a range of other simple gates which can be formed by combinations of those gates. Uh, so the three fundamental logic gates you must have studied in your curriculum. They are AND gate, OR gate, and NOT gate, right? So each gate has its own logic symbol, and that the symbol allows complex functions to be represented by a logic diagram. And Also, the function of each gate can be represented by a truth table or using a Boolean expression or Boolean notation. So fundamentally, these are the things that we study in our curriculum, and we should know them at the top of our mind. Remember, it's not in very complex circuits, memorizing them that the secret lies. You should be very clear with the fundamentals of digital logic design. Circuits like what kind of different circuits, basic circuits that you can create using these gates, like an adder or a subtractor, a latch or a flip flop, common types of flip flops, their comparisons, right? So these are up to this level at least. You should study from your book and revise before your exam, especially if you are an electronics and communication graduate. Uh, Moving on with the basics. What are the common logic gates? As I said, the first three ones are the most important ones: NOT gate, AND gate, and OR gate. Then you start combining these, and you get NOT and NAND, then NOR, then XOR and XNOR, and then there is the buffer gate. So we will just go through these and understand their truth tables and also see their diagrams and symbols. So starting with the first one, AND gate is multiplication and denotes multiplication x y. So it's a two input AND gate, and the output is denoted by Z here. So look at the diagram for the AND gate and the truth table. So XY means you get an output 1 only when both the inputs are 1, because 1 into 1 is equal to 1. Any other combination. So look at the truth table. This is the first one. So let me discuss this in a bit of detail. Uh, and means this operation x dot y, right? So it's multiplication. Denoted by x dot y. You're seeing the diagram as well. So it's a multiplication basically of two variables. So x, y, the two inputs, x into y, 0 into 0, 0, 0 into 1, 0, 1 into 0, 0. But 1 into 1, you get 1, right? So that explains the AND gate. Another one, OR gate, x plus y. So the symbol is plus. And look at the diagram. You should remember these diagrams by heart, not to forget ever. Now look at the output here. It's an OR operation, so it's addition. So it's simple, right? If you have one in any, you will get a positive output. Apart from the fact that if both are zero, then you will get zero, because zero plus zero will not give you anything. You're going to anyways get zero, right? So here, what the logic? Look, let's look at the truth table. The logic that works is that in all other cases, apart from when both are zero, the output is 1, right? And only in cases when both are 0, you get a 0 output. So that is an OR gate. Not gate, look at the symbol, it's slash, it's a slash at the top or on the right hand side. Not and there's a triangle with a small circle at the end, that is the not gate. The buffer is different. Buffer basically buffers and gives you out the output. So let's look at these. Not gate, look at the truth table. If you input 0, it's a single variable not gate, right? So not gate is different from the and or gates. If you put 0, you get 1. If you put 1, you get 0. Unlike buffer where you put 0, you get 0, you put 1, you get 1, right? So these are some common gates. I hope the diagrams and the truth tables, the connection is pretty explanatory here. Moving on to another four gates which we are going to discuss in this session. Look at NAND gate. There is a negation symbol on AND right at the top. So these can be converted into Boolean expressions as well. We'll see an example of Boolean expression after a couple of slides. So how do you make a NAND gate? The same AND symbol, but there is a circle at the end. So it's basically not being applied at the end of the AND operation, right? So what happened in the AND operation, if you remember? In the AND operation, you used to get 1 only when both were 1 and the others were 0. So you are applying a not to it, so basically reversing it. So look at the output Z. The case where AND was 1, that is 1, 1, so that becomes 0, and all the three other cases were 0, so they become 1. So after the end output of the AND operation, then you are applying the NOT operator. So that is the logic. Similarly, look at NOR. X plus Y has a bar above it. So first you do the X plus Y OR operation and then you apply a NOT. So X plus Y OR operation, what was the output? The output was in the truth table 0 triple 1, right? So only in one case when both were 0, it was 0. Otherwise, in any even if one was 1, it was the output was 1. That was OR. So it becomes reverse. So 0 triple 1 becomes 1 triple 0. So you are applying not. Again, see there is a circle at the end of the OR gate. So that becomes NOR gate. I hope these NAND and NOR is pretty simple and the fundamental of applying not at the end of the OR and the AND operation is understood here. Now, exclusive OR and exclusive NOR. Look at the symbols, right? The symbol has the plus sign with a circle over it, and the second one has a bar over that ZOR thing, right? And also note in the diagram that there's a difference. In case of ZOR, on the OR gate, you have sort of a curve before the XY inputs get fed, right? So there is a slight curve XY. See the difference at the time of input, and in XNOR it's a NOR gate and that has a curve in the beginning, right? So that is what it is. So you need to remember the truth table for these as well. So see, look at the first one, ZOR gives an output 1 when either of X or Y is 1, right? Both should not be 0, both should not be 1. That is the point. That's how you remember the truth table here. When both are 0, you get a 0. When both are 1, again you get a 0. Got the point? So, in cases when one is 1 and the other is 0, or 0 1 or 1 0, that is those are the cases in which you get 1. And the exact reverse of it, when you apply a not to it, that is what we call XNOR. In that case, so it becomes reverse, right? When both are 0 or both are 1, that is the case when you get 1. So carefully try to observe this. XOR, at the end of XOR, you apply a NOT that becomes XNOR and the output gets reversed. So what is XOR gate output? XOR gate output is 0 1 1 0, right? So when 1 0 or 0 1 is the case, right, then you get a 1 output, right? So XNOR is the reverse of it. So those two will become 0 and the 0 0 1 1 case that becomes 1 1. So just make these diagrams on your copy once and try to remember them. These fundamental logic gates are very important in trying to express Boolean expressions as well as in making circuit diagrams or trying to learn some common circuit diagrams like flip-flops, adders, subtractors, etc. Right? Okay. So moving on to the next slide here. Now, I've taken a general expression, tried to uh, analyze the truth table by converting that circuit to a truth table. So all these things are related, right? These circuits, truth tables, these diagrams, as you must have understood from going through the gates. So let's have a look at this example. The first one is an AND gate. The second one is also an AND gate. But before the second AND gate, there is a NOT, right? So look at what comes out of the first AND gate on the top. A and B. So you get AB, right? Okay. Now that is visible here, right? So if you move to the next one, when this is the point here, the input is C, so this is fine, but the input here is coming from upside here, right? So it is A, but not A. So this is A dash, right? So this is A dash. So here you have two inputs. One is C and the other is A dash, right? So what comes out is A dash C. So from both these gates, what the input that you are getting, one is A dash C, and the output you are getting, the one is A dash C and the other is AB. And then you are ORing these. So you know the OR operation, right? It's basically addition. So what you get on the output side is AB plus A dash C. So that is the output that has been displayed here. Now you need to convert this into a truth table. This entire Y output that needs to be converted into a truth table, right? Now, how do you make a truth table? Basically, how many variables are there? Just check A, B, and C, right? So there are three variables, so 2 to the power 3. There will be 8 cases. All right. So write down ABC and write down those 8 cases for the potential input combination. Okay. So how does it happen? It's simple binary arithmetic. The first one is 000 100 right? Remember in octal algebra, these are the digits, right? 0 to 7. Okay. So now you check the output. If you look at the output now, look at the first row, all three zero. So all three are zero. So this is 0 into 0, 0. And then this one is 1 into 0 because it is a dash, a bar, which means the reverse. So 1 into 0 is also 0. So the output is 0. Okay. Fine. Now, let me take you to the next one. I'm now looking at row number 2. All right. So, how do we make the truth table? We are trying to understand that. We go to row number 2. When you go to row number 2 and try to apply that same expression, AB is 0, 0. So, this is 0. The first term is 0. Got it? Okay. Now, what about the second term? This is A dash C. So A dash becomes 1 and C is 1. So 1 into 1, 1. So the output becomes 1. Got the point? So I hope this is clear. You basically need to put the values into this after making that basic input combination, 8 cells here, 8 columns here, and then accordingly put here and check. Right? So this is how you convert a circuit to an expression to a truth table, and these all are very related, and you should be very comfortable and confident in applying this kind of a logic if asked. All right. So, having this done all this, let me run you through some typical. If the interviewer might ask you questions on making some gates or some basic diagrams, as I said, this one, this PPT, this lecture is more focused on gates. You should also prepare a bit of flip flops and latches, adders as a practice. But all they follow the same logic, right? So, but let me also run you through some simple placement questions and some theoretical ones and see the answers to them. On this, these are all elementary questions, and you need to understand that at this elementary level, you should be prepared. So you can actually, after this video, go back and take out your books and make basic notes on the different terms that I have mentioned. Many of them I have discussed. Others I'm leaving for you to cover up and revise from your books. So at a basic fundamental level, you should remember these things. That is important. All right. Okay, so the first question, what is the difference between a latch and a flip-flop? Right, so simple answer would do, right? So what's the answer? Latches are level sensitive, while flip-flops are edge sensitive. So this is something that uh, you should be remembering, right? They both can be used in sequential logic and they both require a clock signal. Fine, that is not a difference, but we are just talking about what they are. Further, a practical difference has been given here. Latches are faster than flip-flop because they need lesser logic gates, right? So these things, if you go to the basics of your chapter, you will be remembering them and just superficially look at a couple of diagrams and write down the difference and just move on. So basically, it's like for preparation. Make a two-pager note on this, and you would be good enough to answer in the interviews. That's how it works. You don't need to go through the whole module, right? So quite often in placements, we are under that pressure that how do we revise all the 4 years? Don't revise all the 4 years, all the chapters. Just go through the basics, the basic diagram, the basic difference. That is the kind of focus that you should be keeping. All right, next question. Why did the hexadecimal number system, why is it called the alphanumeric number system? Right. So we know that these number systems in logic design, binary arithmetic, they get formed in powers of two. Like 2 cube is 8, 2 to the power 1 is 2, that is binary, 2 cube is 8, that is octal, 2 to the power 4 is 16, that is alphanumeric, right? So it's called alphanumeric or hexadecimal. It's called alphanumeric because you have, in any base system, the number of digits that are allowed are from 0 to base minus 1. For example, base 2. So you have two digits, 0 and 1, 2 minus 1 tak, right? If it's base 8, it's 0 to 8 minus 1 means 0 to 7. Again, 8 digits, right? Because 0 is also included. If it is base 16, it would be 0 to 15. But if you take digits like 10, 11, 12, 13, 14, 15, you will get confused whether it's 10 or it's 1, 0, a two digit number. Because 0 and 1 are also digits in the same base system, right? If you write 1 5, that's a two-digit number, or is it 15, that one digit in hexadecimal? To remove that communication and to make the nomenclature very unique, right? It is essential that after 9 we start giving alphabet names, and that is why after 0 to 9, 10 becomes A, 11 becomes B, and so on, right? So since we use alphabets and digits both to represent the numbers in the hexadecimal based system, that is the reason why it is called alphanumeric, right? So very fundamental, but something that we should be very clear on why we do it, and how do we do it, right? Okay. So taking another question, what are sequential and combinational circuits? Okay, again, something which is very theoretical and big. You will get these things in the beginning of your chapters. So sequential circuit depends on clock cycles, present input and past outputs to generate the output, right? On the other hand, the combinational circuit is a circuit which is, we can call it time independent circuits, right? They do not depend on time clocks and previous inputs to generate the output, right? So that is the fundamental difference. Again, you can go through the first paragraph and a couple of diagrams on these topics, and you can, if time and the interviewer expects you to draw a basic diagram to explain, you should be ready to do that as well. All right, so the difference again, let's go through it. One has dependence on clock cycles, etc., and the other one is time independent. So that is what the major difference is. Okay, now the last question, it's a very simple question. What are min terms and max terms, right? So these are Boolean expressions. Again, anybody who has studied Boolean expressions and revises it a bit will know that min max terms are product and sum of some form of expressions, right? So a type of Boolean expression where you have a product, right, and where each value appears as, let's say, x or x bar, complement or uncomplement, right, a variable. So that is called a min term. On the other hand, max term is a sum of Boolean expression where the variables appear again in complement or uncomplement form. Now the point here is, again, for min terms and max terms, there are simple calculations and expression solving which is given in the chapters. You should be able to do solve min terms, max terms, and also draw a truth table for them if required. So, and as I said at the beginning, truth table. So you can also be asked to draw a circuit diagram for it, right? So this logic design chapter is very important. But the objective of this lesson was not to cover the entire thing. You can do that from your book. The objective was to give you a heads up on what things are important, and so that you can go back and maybe spend a couple of hours to revise what you have studied in your college curriculum. I hope this is clear and you enjoyed this recap class from the placement perspective. All the best. Thank you.